Somewhere in a lab in Beijing, a tiny metal coin, smaller than a stack of coins, just quietly started producing electricity. And it's going to keep producing that electricity for the next 50 years without ever being plugged into a wall, without ever being recharged, and without ever needing a single drop of fuel added to it. That's not a typo, and it's not a science fiction pitch, and no, it's not going to melt down or give anyone superpowers. It's a real product, already announced, already in pilot production, and it runs on radioactive decay instead of chemistry. While the rest of the world is still trying to squeeze one more hour of battery life out of a smartphone, China just unveiled a battery that could theoretically outlive the person using it. Let's get into how something this small pulls off something this absurd. What exactly is a nuclear battery? Let's clear up the scary part first, because the second you hear the word nuclear attached to anything, your brain probably jumps straight to mushroom clouds and glowing green barrels, the kind of imagery Hollywood has been feeding people for decades. This is not that. A nuclear battery, more precisely called a beta-voltaic battery, doesn't work anything like a nuclear reactor, and it doesn't involve any kind of chain reaction, fission, or meltdown risk whatsoever. It's a fundamentally different piece of physics wearing a scary-sounding name. Here's the actual concept. Certain radioactive isotopes decay naturally over time, shedding particles as they break down into more stable elements. Some isotopes release that energy as beta particles, which are essentially fast-moving electrons. A beta-voltaic battery captures those beta particles using a specially designed semiconductor layer, similar in concept to how a solar panel captures photons of light and converts them into electrical current, except instead of harvesting sunlight, this device is harvesting the natural decay of a radioactive isotope sealed permanently inside it. No moving parts, no combustion, no chemical reaction that degrades over charge cycles the way a lithium battery does. Just steady, continuous low-level electrical output driven by physics that doesn't care whether the lights are on or the temperature outside is freezing or scorching. This concept isn't actually brand new. Beta-voltaic batteries have existed in research labs and niche military and aerospace applications since the 1950s, mostly using isotopes like tritium or promethium in extremely low-power configurations for things like satellite instrumentation. But they've always been stuck in a corner of the industry, expensive, low power, and difficult to manufacture at any real scale. What changed recently, and what China just demonstrated, is a version of this technology built using a completely different isotope and a completely different semiconductor material, one that dramatically improves both the safety profile and the practical power output compared to every previous generation of this idea. It's worth sitting with just how strange this is compared to literally every other battery you've ever owned. Every battery you've plugged in, replaced, or thrown in a junk drawer works through a chemical reaction. Two different materials trading electrons back and forth until the chemistry runs out of gas, so to speak, and the battery goes dead. This thing doesn't have that problem because it isn't relying on a chemical reaction that depletes at all. It's relying on the fact that unstable atoms fall apart on a predictable schedule, whether you're using the battery or not, and that schedule can stretch across decades depending on which isotope you pick. You're not draining a chemical reserve, you're tapping into a physical process that was already going to happen regardless of whether anyone built a device around it. The BV100, meet the battery, that doesn't charge. The specific product making headlines here comes from a Beijing-based startup called BetaVolt, and it's called the BV100. And on paper, it sounds almost too simple to be revolutionary. It's a battery roughly the size of a coin, smaller than most people's thumbnail, and according to the company, it's rated to output continuous power for 50 years without any degradation in performance, without ever needing to be recharged, and without any moving parts that could wear out or fail mechanically over that entire time span. The isotope doing the actual work inside the BV100 is nickel 63, a radioactive isotope of nickel that decays by emitting low energy beta particles. Nickel 63 was chosen specifically because its decay half life sits at just over 100 years, meaning the isotope decays slowly and steadily enough to provide a genuinely long lasting, stable power output without the isotope itself needing to be replenished or swapped out during the device's practical service life. The company has packed multiple modules of this decay layer between ultra thin diamond semiconductor converters, a material choice that turns out to matter enormously for both performance and durability. Here's why diamond specifically. Diamond semiconductors have an exceptionally wide band gap, meaning they can tolerate radiation exposure and heat far better than traditional silicon based semiconductors without breaking down or losing efficiency over time. Diamond is also, famously, the hardest naturally occurring material on the planet, which gives these tiny battery modules a level of physical durability that silicon semiconductors simply can't match, especially for a device that's supposed to keep functioning without any maintenance whatsoever for half a century straight. Betavolt has claimed the current BV100 module can be stacked in layers to scale up both voltage and power output, meaning the tiny individual cell is really more of a building block than a finished consumer product on its own. The name itself is worth unpacking a little because BV100 doesn't stand for anything particularly poetic, it's just a product designation. But the marketing framing around it has leaned hard into the 50-year lifespan number for obvious reasons. 50 years isn't just a big round marketing figure either. It lines up almost exactly with roughly half the decay half life of the nickel 63 isotope itself, meaning the device is designed to still be outputting a meaningful fraction of its original power at the end of that 50-year window, rather than 50 years being some arbitrary cutoff engineers picked because it sounded impressive on a press release. How does it actually work? Step by step. Let's break down the mechanics here because the underlying physics is genuinely elegant once you strip away the intimidating vocabulary. Inside the battery sits a thin layer of nickel 63 isotope material. As that isotope naturally decays over time, the process it undergoes is called beta decay, where an unstable atomic nucleus emits a high speed electron called a beta particle in order to transition into a more stable configuration. This decay process happens constantly and spontaneously, driven purely by the physics of an unstable nucleus seeking stability, requiring absolutely no external trigger, switch, or ignition source of any kind. Those beta particles get emitted in essentially random directions from the decaying isotope layer, and they slam into the surrounding diamond semiconductor material sandwiched immediately around it. When a beta particle strikes the semiconductor, it knocks loose electrons inside the material's crystal structure, creating what's called an electron hole pair. The semiconductor's internal structure is specifically engineered with a built in electric field, similar in concept to the PN junction found in an ordinary solar cell, that sweeps those newly freed electrons in one consistent direction, generating a steady flow of electrical current that can be tapped off through electrodes connected to an external circuit. It's essentially the exact same fundamental principle as a solar panel, just replacing sunlight with the natural decay energy of a radioactive isotope as the input source driving the whole process. Because that decay process never stops on any meaningful human timescale, and because there are no moving mechanical parts, no liquid electrolyte to leak or degrade, and no chemical reaction consuming reactive materials the way a lithium ion battery's charge and discharge cycles gradually consume its internal chemistry, the battery simply keeps producing power continuously without the capacity loss that plagues every conventional rechargeable battery on the market today. Your phone battery degrades a little every single charge cycle. This thing, by design, doesn't have charge cycles at all. There's an important distinction worth making here between this and other radiation based power sources people might already know about, like the radioisotope thermoelectric generators NASA has used to power deep space probes for decades. Those systems generate electricity from heat, essentially letting a radioactive source get hot and using a thermocouple to convert that heat difference into current, similar in principle to how a car's engine block generates usable energy from temperature difference. Beta voltaic batteries skip the heat step entirely and convert the particle emissions directly into electrical current through the semiconductor junction, which makes them considerably more efficient at small scales and far better suited to a device you'd actually want small enough to fit inside a pacemaker rather than bolted onto the side of a spacecraft. Tiny, safe, and genuinely hard to believe. The safety question is obviously the first thing anyone brings up, and it's a completely fair thing to ask about because most people's mental image of anything radioactive involves lead lined containers and hazmat suits. The reality here is considerably less dramatic. Nickel 63 emits beta particles at relatively low energy levels, weak enough that they can actually be fully blocked by a thin sheet of ordinary material. And Betavolt has stated the BV100 doesn't produce any external radiation at all under normal operating conditions, with the decay energy entirely contained and converted within the sealed module itself. The company has also claimed the device is designed to withstand a fairly punishing range of real world abuse without releasing any radioactive material, including exposure to gunfire, being punctured, and temperature extremes ranging from deeply sub zero all the way up past 100 degrees Celsius. Conditions that would destroy or ignite a conventional lithium battery almost instantly. That durability profile matters enormously if you're imagining where a battery like this could actually end up being deployed, because a device rated to survive being shot at and frozen and baked is a device that can go places conventional batteries simply cannot follow. And the size is honestly the part that's hardest to wrap your head around once you've absorbed everything else. The current BV100 module measures just 15 millimeters by 15 millimeters by 5 millimeters, roughly the footprint of a small coin and thinner than most stacks of coins you'd find in a junk drawer. Yet, it's engineered to output steady power for decades on end without any external input whatsoever. It's not powerful in the way a car battery or even a phone battery is powerful. Current output sits in the microwatt range for a single module. But for an enormous category of devices, that trickle of continuous maintenance-free power for 50 straight years is worth infinitely more than a bigger battery that needs to be swapped out every couple of years. Comparisons to lithium batteries are almost unavoidable here, and it's worth being upfront about where this technology genuinely wins and where it doesn't. Lithium batteries store far more usable energy per gram and can deliver it in large, fast bursts, which is exactly why your phone, your laptop, and your electric car all rely on lithium chemistry rather than anything nuclear. A beta voltaic cell trades that raw power density for something lithium simply cannot offer at any price, an output curve that barely declines over an entire human lifetime, with none of the fire risk, none of the capacity fade, and none of the eventual landfill problem that comes from millions of dead lithium cells needing to be collected and recycled every single year. It's less of a replacement for lithium and more of an entirely different tool built for an entirely different job, where this actually gets useful. A battery that produces a steady trickle of power for half a century sounds like a neat party trick until you start thinking through the specific problems it actually solves. And that's where this technology gets genuinely exciting, rather than just impressive on a spec sheet. Medical implants are probably the single most obvious application, and pacemakers specifically have been the dream use case for this exact kind of technology for decades, discussed in academic papers going back to the very first beta voltaic experiments in the mid-20th century. Right now, pacemaker batteries typically need to be surgically replaced every 5 to 15 years, which means every single patient with an implanted pacemaker faces a recurring surgical procedure, along with all the associated infection risk, cost, and recovery time that comes with cutting someone open again just to swap a power source. A battery rated to run for 50 years without replacement could mean a device implanted in someone's 20s keeps working reliably through their entire remaining lifetime, with zero additional surgeries required purely for power maintenance. Beyond medical devices, deep space missions have long struggled with exactly this problem, since solar panels don't work well or at all once a spacecraft travels far enough from the sun, and conventional chemical batteries degrade steadily over the multi-decade mission timelines that deep space exploration often requires. A power source that just keeps quietly producing electricity for 50 years, regardless of sunlight, temperature, or distance from any charging infrastructure, solves a problem that's genuinely limited how far and how long spacecraft can operate independently. Similar logic applies to remote sensors scattered across environments humans rarely visit. Deep ocean monitoring equipment, seismic sensors buried in remote terrain, and military or industrial equipment deployed somewhere that a technician physically cannot reach on any kind of convenient schedule to swap out a dying battery. Microelectronics is another category worth mentioning specifically, because as chips and sensors keep shrinking, their power requirements have been shrinking right alongside them, which means a lot of modern low-power devices genuinely don't need much electricity at all. They just need it reliably and continuously without interruption. Tiny environmental sensors, embedded medical monitoring chips, and miniaturized industrial equipment could theoretically run for their entire operational lifespan off a single sealed nuclear battery smaller than a fingernail, never needing a maintenance visit, a battery swap, or a recharge cable at all. Drones and autonomous sensor networks represent another quiet frontier here, particularly for long-duration surveillance or environmental monitoring applications, where a drone or sensor needs to sit dormant for extended stretches and then activate briefly without the accumulated self-discharge that eventually kills a conventional battery just from sitting unused on a shelf. Military applications get discussed a lot around this kind of technology too, for obvious reasons, since a power source that never needs resupply lines, never needs a soldier to carry spare batteries into the field, and can't be easily detected or jammed the way a wireless charging system might be, solves a genuinely persistent logistical headache that modern militaries deal with constantly. Whether any given country's military actually adopts this specific technology remains to be seen. But the appeal of the concept itself is not exactly subtle, scaling up from coin-sized cell to real power output. Right now, the BV100 in its current single module form produces a genuinely tiny amount of power, enough for extremely low draw applications, but nowhere close to running anything resembling a smartphone or a laptop. Betavolt has been publicly clear that this first commercial version is really a proof of concept and an initial building block rather than a finished universally applicable power solution, and the company has already outlined a roadmap toward significantly higher output versions. The scaling strategy here comes down to stacking. Because each individual module is so physically thin, multiple decay and semiconductor layers can theoretically be sandwiched together into a single package, multiplying the total power output while only modestly increasing the overall physical size of the finished battery. Betavolt has publicly discussed plans to develop a higher output version in the 1-watt range within the next couple of years, which would represent an enormous jump from the current microwatt scale output and would meaningfully expand the practical list of devices this kind of battery could actually power on its own without needing to be paired with a supplementary conventional battery. There's also active research happening around swapping in different isotopes entirely to further improve the power density and cost profile of these devices going forward. Some researchers have pointed toward other beta-emitting isotopes as potential future candidates, each with different half-lives, different energy outputs, and different cost and availability profiles, meaning the current nickel-63 formulation is likely just the first commercially viable version of a technology platform that's going to keep iterating and improving over the coming years, the same way early lithium-ion batteries from the 1990s look almost unrecognizably primitive compared to what ends up in a phone today. Cost is obviously the other half of that scaling equation, and it's the part Betavolt has been noticeably quieter about, for understandable reasons. Producing purified nickel-63 requires nuclear reactor time to irradiate the source material, and fabricating diamond semiconductor layers thin enough and precise enough to sandwich around that isotope isn't exactly a process you can spin up in a garage workshop. Early production runs of any technology like this tend to carry a steep price tag, and the real test of whether the BV100 becomes a footnote or a genuine industry-shifting product will come down to whether Betavolt, or whoever follows in its footsteps, can bring manufacturing costs down fast enough to make this competitive against simply replacing a conventional battery every few years, which for a lot of applications is still the cheaper option today, even with all the maintenance hassle that comes with it. The bigger strategic picture. Stepping back from the specific engineering for a second, it's worth asking why this particular technology is showing up out of China right now. And the honest answer ties back into a pattern that's shown up repeatedly across this channel already. China has been aggressively investing in advanced materials, science, diamond semiconductor fabrication, and isotope production infrastructure, all of which happen to be exactly the ingredients this specific battery technology depends on. Diamond semiconductor manufacturing in particular has historically been an extremely niche and expensive specialty, and having domestic capability to produce that material at meaningful volume is itself a competitive advantage that very few other countries can currently match. There's also a supply chain angle that's easy to overlook. Nickel-63 isn't something you dig out of the ground directly. It has to be produced through nuclear processes, typically by irradiating nickel-62 in a nuclear reactor to transmute it into the radioactive isotope needed. That means a country pursuing this technology at scale needs not just the semiconductor fabrication expertise, but also the nuclear infrastructure capable of actually producing the isotope fuel supply domestically, rather than depending on some other country's reactors and export licenses to keep the pipeline running. China, unsurprisingly, given everything already covered about its nuclear ambitions elsewhere, happens to already have exactly that kind of domestic nuclear infrastructure in place. There's also a research funding pattern worth noting, because this technology fits neatly into a broader Chinese strategy of identifying decades-old scientific concepts that stalled out elsewhere due to cost or manufacturing limitations, and then throwing enough coordinated state and private investment behind them to actually push past those old barriers. Beta-voltaic batteries sat in academic journals for 70 years without much commercial traction anywhere in the world. Not because the physics was wrong, but because nobody had assembled the right combination of cheap diamond semiconductor fabrication, efficient isotope production, and a genuine market need patient enough to wait for a coin-sized cell to prove itself. That's a pattern you could apply just as easily to thorium reactors sitting on a shelf since the 1960s, or geopolymer concrete chemistry known since the 1970s. China keeps finding the old ideas that were correct all along and simply under-resourced, and quietly finishing what other countries started and abandoned. Closing, power that simply doesn't run out. So step back and look at what's actually happening here. A battery smaller than a coin, containing no moving parts, no liquid electrolyte, and no combustible chemistry whatsoever, quietly converting the natural radioactive decay of a nickel isotope into a steady trickle of electricity for 50 uninterrupted years. A diamond semiconductor doing the actual conversion work, chosen specifically because it can survive the exact kind of relentless particle bombardment that would degrade ordinary silicon over that same time span. A device the company claims can survive gunfire, punctures, and temperature extremes that would destroy a conventional battery in seconds, built from the ground up for environments where nobody's ever coming back to swap the power source, and a scaling roadmap already in motion, aiming to push the output from a barely there trickle up toward genuinely useful power levels within just a few years. None of this exists in isolation either. It's sitting on top of the exact same foundation covered across this channel's coverage of China's broader energy ambitions, the same nuclear expertise, the same advanced materials research, the same willingness to take a decades-old academic concept nobody else bothered scaling and actually push it into a real purchasable product. A pacemaker that never needs a second surgery, a deep space sensor that outlives the mission planners who launched it, a piece of remote monitoring equipment buried somewhere nobody will ever physically visit again, quietly doing its job for half a century without anyone ever thinking about it twice. And that's really the story hiding underneath the headline. This was never just about a clever coin-sized gadget. It's about permanently decoupling power from maintenance, building devices that simply stop needing anyone to think about their battery life at all, for longer than most human careers last. Picture the actual consequences of that idea sitting in front of you for a second. A child gets a pacemaker at age 10 and never needs another battery-related surgery for the rest of a full, ordinary lifetime. A sensor gets buried in a remote seismic monitoring station and outlives the engineer who installed it, still quietly reporting data to a grandchild's research team decades later. A deep space probe keeps transmitting long after mission control has moved on to an entirely different generation of hardware back on Earth. None of that requires any breakthrough beyond what's already been announced. It just requires this technology scaling the way its developers say it will, while other countries are still chasing incremental battery life improvements measured in extra hours per charge. China just skipped the entire conversation and built something that measures its lifespan in decades instead. And by the time anyone else catches up, this technology will already be quietly running in devices most of us haven't even thought to look for it in yet.